An op-amp amplifier circuit with electronic gain control is shown in this example, implemented with two operational amplifiers op-amps and two matched JFETs or junction field effect transistors. We want to see how this circuit is working in terms of being able to electronically control the gain of amplifier from V in applied at this point to V out, and also we want to figure out as a function of the V control for the gain control and Vref or reference voltage, what is the gain of this circuit given the two matched junction field effect transistors. To quickly do this, let's make the assumption that both op-amps are properly biased. Let's say plus minus 10 volt supply voltages are applied. At the same time, we can see that for both op-amp, the output is properly connected via circuit to the inverting or negative input terminal, indicating existence of negative feedback. There you go. So for the second op-amp as well, we have connection back to negative or inverting input terminal. So both op-amps properly biased with negative feedback. Therefore, both op-amp are functioning in linear region of operation, not in saturation. As a result, we can say virtual short is valid for both op-amp, which means the voltage at the positive input terminal should be equal to the voltage at negative input terminal for both op-amps. So for example, op-amp 1, positive terminal is grounded, as you can see here. Therefore, because of the negative feedback, the negative terminal is also at input enforced to have 0 volt as well, similar to the positive terminal, effectively forcing the negative terminal to be at virtual ground. The same thing about the op-amp number 2, in which positive terminal is connected to Vn. Because op-amp is ideal, no current can flow through the input terminal of the op-amp because it has practically infinite impedance. So Vin also appears at the positive terminal. And as a result of that, because of the negative feedback, it is enforced that the negative terminal also forced at the same voltage Vin because of the virtual short. So with that in mind, now let's focus on the operation of the first JFET or junction field effect transistor in this example, transistor T1. The gate is here, the source is here, which is exactly the same node as the negative input terminal or inverting terminal of op-amp 1. And it's at 0 volt as well. Whatever current that is flowing through, let's say drain on top, source here, whatever IDS on, so whatever IDS is flowing through this, let's say IDS1, is flowing from the drain of transistor T1 to its source, that current can only go through R1. There is no other route for the current because the input terminal of ideal op-amp cannot have any current because of practically infinite impedance. Now, the value of this IDS1 is controlled effectively by negative V control, which is a negative control voltage, and the value of R1. And the value of R1 here. Because on one side of R1, on one side of resistor R1, we have negative V control. On the other side, we have 0 volt. So effectively, the voltage drop across R1 is known. And if the value of R1 we set it properly. Let's say, for instance, we set the value of R1 to be, for instance, a good example would be 1 kilo ohm. So I'm going to set it here. So 1 kilo ohm as an example. And let's say we limit the V control to be negative V control or negative VC. So I'm going to just stick with the C here. Is a control voltage between 0 and minus 3.5 volt, for instance. Then we are enforcing the current of the drain source for the transistor T1 or JFET T1. What's the benefit of that? Well, the benefit of that is if we go back to IV curve of IDS versus, or the current of drain source of the JFET versus the voltage of drain source, we can see what observation we are noticing. So take a look at this IDS as a function of VDS plot. So on vertical axis we have IDS, or the current of the drain source. On the x-axis we have or horizontal axis we have the voltage of drain source, which is basically the voltage between the. So I'm going to just move this Vref from here so that there is enough space. What I'm talking about is plus minus VDS. So plus minus VDS1, the voltage of drain source for the transistor T1. Let's focus on the ohmic region, which is the region that matters to this example of a gain control. So in this example, transistor T1 or JFET is supposed to be acting as a voltage control resistors effectively. So in that sense, if we set VDS for transistor 1 to around, say, 1 volt, it's a very nice setup. So I'm going to focus on the zoom in version here. But before that, let me show you what's happening to the gate source. So if this is VDS 1 and I said let's set it to 1 volt, here is what's happening. With R1 at 1 kilo ohm and with V control between 0 and negative 3.5, obviously IDS can be easily computed, and I'm going to show it here. So let me just maybe shift this so that it's there is enough space to show the IDS. So IDS 1 is equal to, as I said, the voltage drop across R1 is known, which is 0 minus VC. So it's going to be 0 minus VC divided by the value of resistor. So it's equal to 1 kilo ohm, and VC, given that VC is in this range, we get that IDS 1 naturally between 0 and naturally between 0 and less than or equal, when negative VC is at minimum negative 3.5 volt, then VC is at 3.5 divided by 1K, 3.5 milliamp. So that's the range of IDS1, from 0 to 3.5 milliamp. So what I'm trying to say is IDS, which is this x-axis zoomed in version of this, y-axis zoom in version of this y-axis, is from 0, so from here on the y-axis up to 3.5. This is in amp, so this means 3 milliamp. So up to 3.5 milliamp. So if we focus on setting VDS to 1, basically by setting Vref to 1 volt, I'm going to set the Vref to 1 volt. Since drain is now forced by Vref to 1, source is forced to be at 0, which is the voltage of negative terminal of the op-amp. Therefore, Vref effectively is the VDS1. So when I set Vref to 1 volt, I am forcing VDS1 to 1 volt. So we are here, always. Now, what it means is, depending on where we set the V control, in between 0 and negative 3.5 volt, what is happening is we are moving along this vertical axis. So it means in the ohmic region of operation of the IV curve of the JFET, we are in this range, which we zoom in here, and we see that the relationship between in this range we are talking about, the relationship between the current and voltage of the JFET is a very linear relationship, like either the red one or orange one or the yellow one or the green one or the other different green, and then finally at the lowest the blue one, which we don't get there. So it indicates that because of a linear IV relationship in this deep ohmic region of JFET, then the JFET is effectively acting like a programmable resistor. And the value of that is controlled by VGS, as you can see, because the color, which color we are operating on, given the fixed VDS, is going to be controlled by the voltage of gate source. For example, when gate source is both at 0, because source is fixed to 0, we can't do anything about voltage of source, which is set to 0. Voltage of gate for transistor T1 is controlled by, so voltage of gate is controlled by the output of the op-amp 1. So that can be changed by the op-amp, by the negative feedback. So op-amp will feel that depending on what current IDS1 is being enforced by the value of V control, op-amp is obliged to set the VGS properly, so set the output properly, which means V-gate properly, and therefore set the VGS in a negative fashion so that the expected current is supported for the drain source. For example, if we want to have the least amount of V control at negative 3.5, we are saying the IDS1 is 3.5 milliamp, the max value. That means we want to support this level. Because VDS1 is forced to 1 volt by Vref, that indicates that we need to be on roughly red curve, the max, and that requires VGS to be 0 so that we are on the red curve. So that means op-amp via the negative feedback will arrive at the steady state of setting the output to 0 so that VG is 0 and Vs being 0 result in VGS that is 0, and therefore we are on the red curve. If we start increasing negative VC, for example, to say negative 2 volt, then IDS at that level is 2 milliamp, and we are going down to, let's say, this level, which means then we need to be on a curve like this, which means between the yellow and green, which means VGS, for example, has to be around negative 2.5 volt, between negative 2 of yellow and negative 3 of green. How does it work? Op-amp will understand it quickly via negative feedback and will force the output to negative 2.5 volt, which means V-gate is negative 2.5 volt, which means VGS is negative 2.5 volts. So that's how the circuit is working in terms of guaranteeing that the T1 is in deep ohmic region and therefore acting as a programmable resistor that its value is controlled by the V-gate, which is the output of the op-amp. So that's the summary of operation. I just need to find the tangent of these lines, either the red or the orange or the yellow or the green, so that that tangent will be effectively defining the value of equivalent resistance that is between the drain and source of this JFET. The nice thing is these two JFETs are matched one. When we say matched transistors, it means they are on the same substrate in the same package, benefiting from same junction properties, and they have the same VGS. See, the gate of both T1 and T2 are the same. So whatever VG set is set for both of them. And the source, so G and D, this is transistor 2, so we are dealing with VDS2. So VDS2, and the current is IDS2. Let me just write it here, IDS2, this current. So what happens is VGS for transistor 2 is the same as VGS for transistor 1 because they have the same gate and they have both sources at 0 volt. Here is actual 0, true 0, and here is virtual 0 enforced by the virtual short of the op-amp. So VS1 0, VS2 also 0. So therefore what I'm trying to say is VGS is the same for both JFET's matched transistors. Okay, so with that in mind, we can now proceed with just calculation quickly. I'm going to remove these curves now that we understand how things are operating. So I'm going to remove this VDS curve, ID versus VDS, and I'm going to continue with my calculations. Okay, so it's a quick calculation now that we understand how the circuit is working. And by quick calculation, I mean this calculation here. So I'm going to say, all right, I already found that IDS1 is equal to VS over R1, VC over R1. VC over R1 is IDS1. That's what I need. Now, if what I need to, as I explained, the transistor JFET is in deep ohmic region and is acting like a resistor. To find the equivalent resistance, I need to divide VDS by IDS1. So that's the meaning of equivalent resistors. So I'm going to say RDS for transistor 1 is equal to VDS1 in this deep ohmic region divided by IDS1. But VDS1 is just Vref, 1 volt. So Vref has to be small, as I showed you on the IV curve, because if VDS is not small, then if VDS is not 1 or 1.5 volts, then you end up selecting VDS large when we get into a region of the IV curve that is not linear. So that's the reason we should avoid Vref above, let's say, 1.5. So I selected Vref to be 1 volt. That's a good value to be selected. So let's say Vref is 1 volt, for instance. And then I can say VDS1 is Vref, and then IDS1, as we found, is VC over R1. So basically we end up with R1 times Vref divided by VC, V control. Okay, so that's the value of RDS1. How do we find RDS2? Well, this transistor T2 is also in deep ohmic region for the same reason explained. I just said that VGS2 and VGS1 are the same. So VGS1 and 2 are the same. Therefore, both, because of VGS2 and 1 the same, going back to that IV curve, when VGS is the same, then both transistors, so let's say if you're on the orange one, if VGS, for instance, is -1 the same, both transistor T1, T2 are on the same curve, so it means on the same IV plot, let's say orange one. So we are on the orange one, and therefore we are in deep ohmic region for both of them. So both of them are observing, let's say, a resistance like this. So same equivalent resistance, but they are operating at different points. Transistor T1 has a VDS1 defined by Vref. But transistor T2 might have a VDS here, might have a VDS here. So basically what I'm saying is transistor T2 has a VDS range that can be in this range. So, but it is on the orange, same orange curve, let's say in this example, as T1, because their VGS is the same. So I would say, since VGS1 equal to VGS2, both transistors or both JFETs are on the same, or both have the same, both JFETs have the same IDS VDS curve. So meaning they have same RDS1 or equivalent resistance in the deep ohmic region, RDS. Given that they are matched transistors. So with that in mind, therefore, now that I found RDS1, I can say this is also equal to RDS2. Now we are done, because with the transistor 2 in deep ohmic region setup, which requires Vin to be a small value, so that also is the thing, because Vin appears because of virtual short, Vin appears at the negative terminal or enforced by the negative feedback, which then becomes the VDS. This Vin at the drain effectively defines the VDS of transistor 2. To guarantee that we are in proper deep ohmic region, we need to make sure that VDS2, which is Vin, is in the small range. So I would enforce, which is good enough, because usually we are in the amplifier, Vin is not supposed to be a large number. So I'm going to write it here. Vin, let's say, has to be between 1, just as a precaution, and let's say, just as an example, 0. So with that in mind, then we are satisfying all the requirements. RDS1 is equal to RDS2, and the value is defined for the programmable resistor that this one is. Now, T2 being a programmable resistor, we can define this stage as a non-inverting amplifier, because Vin is applied at the positive terminal, and then we have the gain stage here. So I'm going to model this second stage as a non-inverting amplifier now, which looks like this. So we have the op-amp number 2. We have the Vin at the positive input terminal. I don't care about RP because it doesn't have any impact on the gain side. It's just for matching. And then we have the connection here, R2 to output Vout. I don't care about RL in terms of defining the gain in this circuit, because gain is not defined by RL. Gain is defined by R2 and equivalent resistance for this transistor. So for that transistor, I'm going to show the equivalent resistance this way. So RDS and then grounded. There you go. So this is a simple non-inverting amplifier. The gain is well known. It's effectively quickly just writing it, but I can quickly also show it using just KCL at the inverting terminal. But effectively it's like this. Vin is here because of virtual short guaranteed. And then we can say there is no current going this way or coming out, so whatever current is flowing through R2 should continue going through RDS, which means RDS and R2 are effectively in series, and therefore relationship between Vout and Vin here is just a voltage division. So I can say Vin is at this node is equal to the voltage drop across RDS, which is then RDS divided by RDS plus R2 times Vout, which is exactly the famous gain relationship for gain formula for the non-inverting amplifier, which is this one divided by RDS plus R2 divided by RDS, which becomes 1 plus R2 divided by RDS. So this is written using KCL or Kirchhoff current law at this node that basically says at the inverting input terminal that says this current should be equal to that current. Incoming current should be equal to the outgoing current. Alright, in this equation now, I'm going to substitute RDS with the formula we found, which is this value. So if I do that, then the gain or AV, amplifier voltage gain, is equal to 1 plus R2 divided by, so R2 divided by RDS. I'm going to substitute using equation 1, which says substitute that with R1 Vref V control. So in summary, we got to gain, which is V out over V in. This is gain, voltage gain, is 1 plus R2 over R1 times V control over Vref, which is 1 volt. So there you go, we got it. So it means the gain of amplifier AV is a function of the value of R1 and R2 that are fixed, for example, and also the voltage control that we can electronically adjust, and a fixed Vref. So, and you can see that the AV is linearly proportional to VC. So effectively we have a nice electronic gain control in this op-amp amplifier defined by simply the V control that is applied at inside the circuit using two JFET transistors. I hope that this example is helpful in terms of showing how we can use JFET transistors combined with op-amps in deep ohmic region to realize a variable controllable resistor that enables us to design an op-amp amplifier with electronic gain control. I hope this is helpful.